Splicing and measuring fiber optic connections. Sendun SD-9 Plus Fiber Splicer. This tutorial presents the operation of the fiber splicer during splicing optic fibers of different standards. The attenuation of the splices will be measured by performing a two-way measurement with a professional reflectometer. In the test, a universal cable with fibers in the G.652.D standard was used, which will be spliced with fibers of three types of cables. The first is an underground DAC cable containing fibers in the same standard. The second is a flat FTTH cable with G.657.A1 fibers. The third is a self-supporting ADSS cable with fibers in the G.657.A2 standard. For each type of connection, two welds will be made. For practical reasons, one end of the cables was placed in a distribution panel installed in a rack cabinet. To terminate them, the same fiber splicer was used with pigtails. The other ends of the cables were inserted into a splice box, protected with a heat shrink sleeve and installed in holders. The test includes 6 welds. Red and white fibers of the universal cable will be connected to the corresponding DAC cable fibers, blue and orange fibers with the fibers of the flat FTTH cable, and green and violet fibers with the fibers of the ADSS cable. Part 1. Splicing. It's time to prepare the fiber splicer. The set offered with the Sendun SD-9 Plus Splicer includes, among other things, a cleaver, equipped with a waste container and an automatic blade rotation mechanism. Also included is a universal fiber stripper and a metal tray on which the welded sleeves are placed for consolidation and cooling. The first step in the entire process will be to remove the pre-measured fibers from the splice cassette. The fiber length allows for proper positioning of the welds in the holders. The cassette also contains fibers that will not be spliced. The extracted fibers are divided into groups. On the left side, the fibers of the underground cable FTTH and ADSS are laid. On the right, the universal cable fibers. Time to start up the splicer. The device is operated using buttons or the touchscreen. The following sections include history of performed welds with their attenuation and parameters of the electric arc used in the welding process. Basic options menu, where you can set, among other things, the date, time, sound notifications, and the function of automatically starting the oven after it is closed. Welding programs menu containing 42 presets for welding various types of fibers. The default is the automatic program, where the welding machine independently evaluates whether the fibers are single or multi-mode. For the first 4 welds, the fully automatic program was used. In the final stage, during splicing G.652.D with G.657.A2 fibers, a preset intended for this purpose will be used. The oven menu allows you to choose the heating program. This is done by selecting the appropriate sleeve length. The sleeves included with the splice box are 50 mm long. Each program is editable. It is possible to modify the oven's working temperature and the time for a single cycle. Here, the heating time was shortened from 30 to 25 seconds. The maintenance menu includes functions used in later stages of operation, for example, during electrode replacement. There is also an option for electric arc calibration. The information card includes, among other things, the serial number of the welding machine, the installed software version, and the device's mileage. The User Options menu allows you to turn on or off functions related to the automation of the welding process. You can control whether this process should start automatically after closing the cover and whether subsequent stages should be confirmed by the user. The last icon is for exiting the menu and entering operations mode. The previously set welding and heating programs are visible at the top of the screen. It is good practice to calibrate the electric arc before welding. It should be performed regardless of the number of subsequent splices in the session. The procedure allows adjusting the parameters of the electric arc to the environmental conditions at the installation site. To carry out the calibration process, you can use the fibers that will be spliced shortly. You can use other fibers as long as the fiber type is the same. The first step is to strip the fiber of its 250 micrometer acrylic coating over a distance of 3 to 4 centimeters and clean it of acrylic residues using a dust-free cloth dampened with IPA alcohol. Then, the fiber is placed in the cleaver in the corresponding V-groove for its diameter. The fiber is broken and the cutting is discarded in the container. The fiber is placed in the welding machine holder and in the blue V-groove in such a way that the fiber end is halfway between the V-groove and the electrodes. When placing the fiber in the welding machine, ensure that its end does not touch any parts. The fiber position is locked with the holder flap. Proceed similarly with the second fiber, which is placed in the second holder. To start the calibration procedure, enter the device menu, select the maintenance submenu, and enable the arc adjust function. Calibration is started with the set button on the housing or the welding machine screen. The entire process takes a few seconds. The welding machine generates an electric arc, melting the fibers. The device analyzes the behavior of the fibers at a given arc power and makes any necessary adjustments. The end of the procedure is confirmed by a relevant message on the screen. Now you can start the actual welding. In the first stage, the fibers of the universal cable will be connected to the fibers of the orange underground DAC cable. Both cables contain fibers in the G.652.D standard. It's time to prepare the red and white fibers, according to the previously presented connection diagram. Next, on one side, the splice sleeves should be put on. The process of preparing fibers for splicing is identical to the calibration process just performed and includes stripping, i.e., removing the acrylic coating from the fiber, cleaning with a dust-free cloth dampened with IPA alcohol, cutting, and placing it in the welding machine holder. Proceed similarly with the second fiber, which is placed in the second holder. The welding machine operates in full automatic mode. After closing the cover, the welding process starts automatically and is not interrupted at any stage. Sendun SD-9 Plus has a large optical magnification, allowing the analysis of the welded fibers. In this case, both fibers are made in the G.652.D standard. The distribution of bright and dark fringes related to the refraction of light passing through the fiber is practically the same. The middle fringe corresponds approximately to the position of the core inside the fiber. Thanks to it, the welding machine properly positions the fibers relative to each other. The attenuation estimated by the welding machine was 0.01 dB. At the splice site, a delicate dark fringe is visible. It may seem like a minor detail, but it's worth paying attention to. Due to the good optical system, the Sendun SD-9 Plus allows relatively easy detection of such phenomena. Sometimes these anomalies will require re-welding, or, as here, they will only be a visual effect, related to a large difference in the refractive index of the two fibers. In such a situation, next to the dark fringe, you should look for a much less noticeable bright fringe. Such a setup indicates that light, passing transversely through the weld, is refracted towards the fiber with a higher refractive index, hence the darker and lighter spots. This phenomenon does not affect the attenuation or the quality of the splice. One should be cautious in assessing such phenomena. So-called underheated splices, or air bubbles in the splice, related to poor cutting or fiber contamination, may look similar. In case of any doubts, calibrate the electric arc if it was not done, and repeat the weld. If the effect persists, the culprit is most likely a different material or a different mode field diameter of the fibers. In this case, this phenomenon occurred for fibers for which manufacturers declare the same standard. The multitude of manufacturers and different production processes mean one should be prepared for various surprises. The completed splice must be protected. The heat shrink sleeve is slid over the fiber connection. Then everything goes into the oven, which turns on automatically after the chamber is closed. The heating process, set for 25 seconds, gives time to prepare the next fiber. After heating, the sleeve is placed on the tray to allow time for consolidation and cooling. The procedure for the white fiber is identical. In the second stage, welds will be made on the orange and blue fibers. These will be connections of the G.652.D universal cable with the G.657A1 flat cable used in multi-family buildings. Despite different standards, the fringe distribution on the fibers is practically the same. G.657.A1 fibers are fully compatible with G.652.D fibers, and generally, their construction will be very similar. The attenuation estimated by the welding machine was 0 dB. The connection point is clean this time and free of any anomalies. The procedure for the orange fiber is identical. In the third stage, splices were made on the green and violet fibers. These will be connections of the G.652.D universal cable fibers with the G.657.A2 self-supporting cable fibers. The splicing mode was changed to a program for splicing standard fibers with reduced bend radius. This change is not crucial. It would be possible to continue welding in auto mode or SM auto. It is recommended to test different modes to find the best one for the given situation. In the case of splicing G.652.D fibers with G.657.A2, you can see the difference in the distribution of bright and dark fringes on the fiber. This is due to the different construction of the fibers, specifically the different refractive index profiles. This profile for the G.657.A2 standard is slightly more complex, allowing the fibers to have a smaller minimum bend radius. These fibers have a smaller mode field diameter, which is the area where the transmitted signal propagates. This is visible with precise reflectometric measurements. The splice site is perfectly visible. After making 6 splices, everything, along with the fiber reserves, is arranged in the splice box. The splices are placed in holders, which prevent the connections from moving. Part 2. Reflectometric measurements. Time to check the splices with a reflectometric measurement. Since different fibers were welded, the reflectometric measurement, performed from the side of the fiber with a smaller mode field diameter towards the fiber with a larger mode field diameter, may result in a false signal amplification at the weld. According to industry standards, measurements were taken in both directions, and the final weld attenuation value will be calculated as the arithmetic mean. For measurements, the EXFO FTB-200 reflectometer with a current calibration certificate was used. Measurements were taken for wavelengths of 1310 and 1550 nanometers. The length of the measured optical paths, including the launch fiber, will not exceed 350 meters, so the measurement range was set to the minimum for this version of the reflectometer, which is 1.3 kilometer. The pulse width was set to 30 nanoseconds. This will ensure a clean, noise-free reflectogram. The dead zone generated by such a pulse will not be an issue, as the weld is preceded by several tens of meters of fiber, regardless of the measurement direction. The averaging time was set to 30 seconds. The end of the measured line is an SC-UPC connector, which, polished straight, causes significant light reflection. This reflection can unnecessarily obscure the reflectogram. To limit the reflection at the end of the line, it was extended using a short SC-UPC, SC-APC patch cord. This fact has no significance for the accuracy of the measurements taken. It's time to start the measurement. In this case, for both wavelengths, the procedure takes about a minute. The measurement from the side of the universal cable did not register an event at the weld location for a wavelength of 1310 nanometers. The weld should be searched for between event number 2, which is the end of the launch fiber and the beginning of the measured line, and event number 3, which is the end of the measured line. The entire measured line is 94 meters, 50 meters of universal cable fiber and 44 meters of underground cable fiber, and it is registered as one continuous section. For a wavelength of 1550 nanometers, the weld was registered as event number 3. Its attenuation is 0.075 dB. This indicates a false signal amplification and suggests a smaller mode field diameter in the underground cable fiber, despite the identical standard as the universal cable fiber. The splicer indicated different refractive indices for these fibers. Splices made on these fibers will be visible in bidirectional measurement and may look similar to splices made on fibers of different standards. The next measurement was taken in the opposite direction. This time, the splice was registered for both wavelengths. Its attenuation was respectively 0.155 dB for a wavelength of 1310 nanometers and 0.141 dB for a wavelength of 1550 nanometers. Thus, ultimately, the attenuation of the first weld was 0.08 dB for a wavelength of 1310 nanometers and 0.03 dB for a wavelength of 1550 nanometers. It's worth reminding once again that the weld attenuation is calculated as the arithmetic mean of the attenuation measured in both directions, sign included. In the second step, a bidirectional measurement of the weld attenuation on the white fiber was made. Again, this is a connection of fibers in the same standard, G.652.D. The recorded attenuation values or false signal amplification for both wavelengths are noted in the table. Ultimately, the measured weld attenuation was 0.04 dB for a wavelength of 1310 nanometers and 0.07 dB for a wavelength of 1550 nanometers. Both splices should be considered as very good. Depending on the assessment criteria, which may be the operator's internal standards, structural cabling standards, or the recommendations of structural cabling system manufacturers, the maximum splice attenuation can range from 0.1 to even 0.3 dB. Most often it will be 0.1 or 0.15 dB. The second section of measurements is tests for universal flat FTTH cable connections. As before, a bidirectional measurement was made, this time for the blue and orange fibers. The fibers connected are made in the G.652.D and G.657.A1 standard. The length of the measured path is 114 meters this time. According to the theory, false signal amplification at the weld when measured from the side of the G.652.D fiber is much more likely than when connecting fibers in the same standard. Indeed, we obtain such results, but the measurement discrepancy resulting from different mode field diameters is no greater than before. These splices on the Splicer screen looked even better than the splices made on the same fiber standard. After saving the results in the table, it's time to analyze the orange fiber. Ultimately, the measured attenuation of both welds was 0.01 and 0.06 dB for a wavelength of 1310 nanometers and 0.07 and 0.02 dB for a wavelength of 1550 nanometers. Both welds should be considered as very good. The last stage is the measurement of two splices made on the green and violet G.652.D and G.657.A2 fibers. Due to the potentially large difference in mode field diameters, the the expected attenuation values and false signal amplifications may be the greatest here. The length of the measured path is 155 meters this time. Measurement towards the G.657.A2 fiber as expected results in a large false signal amplification at the weld. The measurement in the opposite direction shows significant attenuation. It should be remembered that the final weld attenuation is the arithmetic mean of both measured values. It's time for the last set of measurements, which were made for the violet fibers. During the last measurement, a much higher reflectance value was noted at the launch fiber connector. Although it does not significantly affect the weld attenuation measurement, it was decided to clean the launch fiber connector and the connector in the distribution panel, and then the measurement was repeated. Cleaning had a positive effect. The connector parameters improved significantly. For the last violet fiber, slightly worse results were obtained than for the green fiber, respectively, 0.11 and 0.12 dB. Given the different fiber standards, these results should be considered as very good. Connections of fibers in these standards practically do not occur in trunk installations, but they can be found in subscriber connections, where slightly less stringent standards apply regarding the performed welds. Sendun SD-9 Plus Fiber Splicer is fast and convenient tool, creating durable splices with good transmission parameters, regardless of the cables and fibers used. An experienced user will appreciate the large screen and the high magnification optical system, allowing for a preliminary assessment of the spliced fibers, cut quality, fiber cleanliness, and detection of potentially dangerous anomalies immediately after splicing. Thank you for your attention. Please visit our online store.